For this lesson, we are going to talk about probability. We're going to talk about all of the vocabulary associated with probability and get some early examples of working with probability out of the way. So, what are some definitions we're going to need? First definition we're going to need is the definition of an event. And an event is a procedure, or basically another way to think about it is an event is something I do. Like flip a coin. Right, I could talk about the probability of getting heads, the probability of getting tails when I flip a coin. The event is flipping the coin. The next definition is sample space. And sample space is all possible outcomes of an event. So if the event is still flipping a coin, then what could happen when I flip a coin? Well, when I flip a coin, I could either get heads or I could get tails. And you'll notice that I'm using these curly brackets here. This is set notation. So I'm just putting in these curly brackets a set of all the possible outcomes of flipping a coin, either getting heads or getting tails. Even more important than the sample space itself is the size of the sample space. The size of the sample space is what we're going to be using when we compute probabilities. And this is just the number of outcomes in the sample space. And for this example, it would be 2, right? Heads, tails, that's 2 possible outcomes. Finally, what do I mean when I say an outcome? An outcome is just the result of the event. So the outcome is either heads or tails. Okay, let's take a look at a more concrete example. Let's talk about rolling a die. So the event here is going to be to roll the die. And you're probably familiar with dice. Remember, a die is a 6-sided cube, and you can get any of the numbers 1 through 6, and they're all equally likely. So that kind of brings us to the next part, the sample space. What are my options when I roll a die? I can land on 1, 2, 3, etc. 4, 5, 6. Any of those are options when I roll a die, and all of those for a die are equally likely. Now, what is the size of the sample space? How many options do I have? I have 6 options. And here are some possible outcomes when I roll a die. One possible outcome would be that I roll a die and I get a 5, or I should say, roll a 5. Another possible outcome would be I roll a die and I roll an even number. I could roll the die and get a number less than 3. And finally, maybe the same thing or maybe different, I could roll the die and get a number at most 3. So we'll talk about whether those 2 different outcomes are different in a minute. But for now, what we're going to do is we're going to compute the probability of each of these 4 separate outcomes. So let's take a look at the first one. All right, so my first outcome is to roll a 5. And here is our introduction to how we actually find probability. The probability of an event is On the bottom, we have the size of the sample space in the denominator, and in the numerator, we have the number of satisfactory outcomes. So this is what it means to be a probability. This is how I compute my probability. So for rolling a 5, how many different ways can I roll a 5? If there are 6 different faces of the dice, only one of them gives a 5. So the probability, and I'm writing this P of 5, that's function notation for probability, or I could write it P of rolling a 5, either way. And this is going to be the number of satisfactory outcomes, which is just 1. There's only one way to get a 5, and the size of the sample space is 6. So the probability of rolling a 5 is 1 out of 6, which you probably knew already. All right, now let's try the probability of rolling an even number. So remember, probability is just going to be, for the denominator, the size of the sample space, and for the numerator, the number of satisfactory outcomes. So let's check here. What are my satisfactory outcomes? What would I be happy with if I'm looking to roll an even number? Well, 1 isn't even, so that wouldn't work. Oops. But 2 would work. Not 3, but 4, and not 5, but 6. Those are my even faces of the dice. So to roll an even number, there are 3 satisfactory outcomes. So I might write this as P of even, and the size of the sample space is still 6, and there are 3 satisfactory outcomes. So this is going to reduce down to 1/2. P of even is 1/2. All right, now let's take a look at another example. Let's find the probability of rolling a number less than 3. So what faces on the die would be less than 3? My satisfactory outcomes. Anything less than 3, that's just 1 and 2. So P of roll less than 3. And notice how in this notation, I'm just saying the probability of, and that those parentheses are the same as function notation, just saying of, what do I want? P of rolling less than 3. And remember, this is just going to be number of the outcomes that we want, number of satisfactory outcomes divided by size of sample space. You can see this is pretty bulky to write out every time, so probably won't write it out again. But okay, let's see. So probability of rolling less than a 3, there are 2 satisfactory outcomes. 6 is still the size of the sample space, so when I reduce this, the probability is 1/3. You always want to reduce. Fully reducing is always a good idea when you're working with fractions. Basically, unless you're instructed not to, you want to assume that you should. So finally, we're going to do our last example of the dice. And that is, I want the probability of rolling at most 3. So P of roll at most 3. And is this going to be the same as rolling less than 3, or is this going to be different? So let's see. Satisfactory outcomes. Well, rolling a 1 is definitely going to work. Rolling a 2 is going to work. How about rolling a 3? Is 3 at most 3? And the answer is yes. 3 is at most 3. If I were to try to go 4, that'd be too big. But there are actually 3 satisfactory outcomes, 1, 2, and 3. So the number of satisfactory outcomes is 3. The size of the sample space is 6. So the probability here is 1/2. And notice that all of these probabilities have been between 0 and 1. And why is that? Because all probabilities are between 0 and 1. There is a reason that I blew this up so big that if I blew it up any bigger, the text would not have fit on the page. All probabilities are between 0 and 1. In college, I had an instructor who told me that I was taking a probability class, and he said, if you get a probability that is less than 0 or bigger than 1, minus 500 million points. He said I'd have to retake the class 6 times to get myself out of the hole. This is a joke, of course, but the idea is, hey, all probabilities are always between 0 and 1. Or if you want to look at it this way, probabilities are always between, I can write between 0 and 1, or I can write them as percents if I want, between 0% and 100%. But the idea is if you get a probability that's less than 0 or bigger than 100%, you have a problem. Something has gone wrong. Okay, now in terms of dice, I should mention the dice example was looking at something called classical probability. And the idea was I knew exactly how many faces there were to the die. I knew exactly the size of the sample space and the probabilities. That's classical probability. The other concept we're going to talk about in this lesson is empirical probability. And empirical probability is just saying, I don't know for sure the size of the sample space or the probability of each event outcome happening, but I do have data, and I'm going to create my probability based on data that I have. So here is our last example. In a recent year, there were 3 million skydiving jumps, 21 of which resulted in death. Find the probability of dying while skydiving. So apart from being a little morbid, this is empirical probability, meaning I'm going to get my probability based off of data that I have gathered. So remember, probability is a perception of dying while skydiving. Whenever I do this example in class, I always get a bunch of awkward chuckles. Okay, so probability of dying while skydiving. The size of the sample space is the 3 million. That is the number of skydives that we know about, so that's all we got. And the number of satisfactory outcomes, and remember, satisfactory doesn't necessarily mean good, right? I don't want to die while skydiving, but since I want the probability of dying, then dying is the outcome I'm looking for. So 21 deaths. All right, so that is the probability of dying while skydiving. Now let's say we also want to write this not just as a fraction, but let's say we want to write this as a decimal and as a percent. By the way, this is not a reduced fraction, but you know what? Let's worry more about getting this as a decimal. So let's go to Desmos, www.desmos.com, and let's find our calculator there. So Desmos Scientific Calculator, and I type in 21 divided by 3 with 6 zeros. Aha, and when I hit enter, I get something that doesn't look like a decimal. This is 7 times 10 to the negative 6. So this is something you're going to learn right away whenever you work with probabilities in calculators. Sometimes you're going to get scientific notation. So we see 7 times 10 to the negative 6, right? There we go. And this is scientific notation. We want to transition this into standard notation, which is just a regular decimal. So what this tells me is that this is 7. Pardon me. This is 7, here we go. And currently the decimal place is there. And I need to move the decimal place 6 times. And since this is a decimal, a probability, something small, I'm going to move the decimal place 6 times to the left. And it's also the negative. So negative means move decimal to left. The negative power in particular, right? This negative 10 to the negative 6 tells me to move the decimal place negative 6 or 6 times to the left. So 1, 2, 3, 4, 5, 6. And there's my new decimal place. What do I do with all the rest? Just fill it in with zeros. 0, 0, 0, 0, 0. There we go. So the standard notation here is 0.000007. Notice that it's not 6 zeros, but it is 6 times that I moved the decimal. And if I want to finally convert this into a percent, remember I just swoop, swoop. I move the decimal place twice to the right. Swoop, swoop. And we get 0.0007%. So if I want this answer as a percent, it's 0.0007%. So finally, here is the bonus question. Is this probability of 0.0007% enough to make you change your mind about skydiving? So there's the bonus question for this video. We are at the end. We've learned about classical probabilities, empirical probabilities, what is a sample space, how big is the sample space, and the question here I'm finally asking is this probability going to be enough to make you change your mind? So some probabilities are big enough to make you think about it, and some probabilities are not. And I would go ahead and wager a guess that if you want to skydive, 0.0007% is not enough to change your mind. And if it was enough to change your mind, then you probably didn't want to skydive like me. It's never gonna happen. So there is the idea of basic probabilities. And remember, all probabilities are between 0 and 1.